Quadratic functions in vertex form is the first actual lesson that we're going to do. And the first thing we need to think about is, what is a quadratic function? We talked a little bit about this yesterday. Two things that kind of define a quadratic function. The equation has a degree of 2, which means it has an x squared in it and no higher power of x. So it doesn't have an x to the power of 3 or an x to the power of 4 or anything like that. X to the power of 2 is the highest power of the variable. That makes it quadratic. And the shape of the graph is a parabola. So this means has an x squared. And a parabola, remember, it's kind of that V shape, but it's not a pointy V, it's curved at the bottom. This is the vertex form for a quadratic function. It's the same as you had on that sheet that I gave you yesterday. Y equals ax minus p squared plus q. If you look at the ones on your sheet, there's a number in the place of a, there's a number in the place of p, there's a number in the place of q, but they all should look basically like that. We're going to look at two different forms. We'll also look at the standard form, which has an x squared term and an x term. But this is vertex form, and this is the one that's most useful. All parabolas can be thought of as transformations of y equals x squared. So y equals x squared is the very first one that we looked at. It's a parabola with its vertex at 0, 0, opens up. That's basically what y equals x squared is. If we change the parameters, which are the a, p, and q in the equation, we change the way the graph looks. And that's what you should have discovered yesterday. If we put a different number in there for p or q or a, the graph looks different. For y equals x squared, a is 1, p and q are 0. So that's why it just looks like y equals x squared. They still have a, p, and q it still has a, p, q, and values, but you just don't see them. So we're going to look at that a parameter first. And I have a couple of graphs here. The first one I have y equals x squared is that red graph, and y equals 2x squared is the blue graph. And how are they different? So that made the graph narrower. And like I was saying, if you put a bigger number than 2 in front of the x squared, it just makes it more and more narrow. The bigger the number, the more narrow it is. If you put in a number that's between 0 and 1, so like 1/2 or 1/4 or 0.3, something like that, then it's going to make it wider. The other thing is with the a, if you look at the second set of graphs, so you're looking over here, this red one, that's just the regular y equals x squared. The green one, it's kind of hard to see, but that's y equals negative 0.5 x squared. So it's a 0.5, it's wider, but because it's negative, it flips it, it changes the direction of the opening. So now we have to answer or fill in these blanks at the bottom. If a is greater than 0, so that means if it's a positive number in front of the x squared, the graph opens, what would go in that blank? Up. And if a is less than 0, the graph opens down. So that's the first thing. The other part of this is what I was talking about with it being narrow or wide. If a is greater than 1 or a is less than negative 1, so that means a would be something like 2, 3, 4, 5, or negative 2, 3, 4, 5, or some other number in that range, then the graph is narrow compared to y equals x squared. And if a is between negative 1 and 1, then the graph is wide compared to y equals x squared. The p parameter. So remember, we're talking about vertex form, which is y equals a x minus p squared plus q, and we're talking about the p parameter, so this number here. The first set of graphs that I have up there, which you probably can't read from where you are, but they're y equals x squared. The red one is y equals x squared. The purple one is y equals x plus 5 squared. So it's a graph where the a value is 1, so it's not going to be any wider or narrower than the first one, but it has that plus 5 in the place of p. And what happened to the graph? It's moved to the left. And in the second set here, we have y equals x squared, and then we have the yellow one is y equals x minus 3 squared. And what happened to that one? Moved to the right. And how many did it move to the right? 3. And the other one, when we said move to the left, moved 5 to the left. So changing that p value changes where the vertex is. It either moves it to the right or moves it to the left. So when we look at the first one, y equals x plus 5 squared, this is actually y equals x minus negative 5 squared, if we're thinking of it in terms of that vertex form, x minus p squared. So this is x minus negative 5 squared, because the two negatives make it a positive, right? But we're actually subtracting negative 5, which means for this one, p is equal to negative 5, and what happened to the graph? Went to the left 5. So if p is less than 0, the graph is moved to the left. And I'm actually going to say moved p units to the left. The reason why this is tricky is because you see x plus 5 and it's moved to the left, and then we say that p is less than 0, even though it says x plus 5, and it's because of that minus a negative number, subtracting a negative number. What you really need to be able to do is look at the graph and know that if it's an x plus 5 or x plus something, it's going to the left. But this is kind of the correct terminology for it. So if p is greater than 0, the graph is move p units to the right. Two other observations: that x equals p is the axis of symmetry of the parabola, and p is the x value of the vertex. But you have to remember that p, it's the opposite of what you see in the equation. If you see a positive, then the p value is negative. If you see negative, then the p value is positive. So the q parameter, this one should be easier because it doesn't have all that positive, negative, weird stuff to deal with. The first set of graphs there, I have y equals x squared, and then y equals x squared plus 4. So it's not a p value now, it's not x plus 4 squared, it's x squared plus 4. So 4 is the q value, and what happened to that first graph? Moves it up vertically, yeah. 4 units, right? The other one, we have y equals x squared, and then y equals x squared minus 6. And what did the graph do? Down 6 units. So this is a little bit easier. The first one, the q value is equal to 4. And if q is greater than 0, the graph is moved up 4 units. If q is greater than 0, the graph is moved q units up. Whatever that value is that's added or subtracted to the end, well, that's added to the end, really, that's going to tell you how far it's going to move. If q is less than 0, the graph is moved q units down. So if it's a number that's subtracted on the end, it moves down. If it's a number that's added, it moves up. That's probably easier to understand than the p parameter. What are your other observations about q? So q is the maximum or minimum value, and it's the y value of the vertex. Here we have two quadratic equations in vertex form. And I just want to know, we're going to do more than just this, but determine the vertex. So if we look at that first one, y equals -3, x minus 1 squared minus 4. Write down what you think the vertex is. The vertex of the first one, who would like to share their answer? 1, -4. So the kind of trick with the vertex is it's the p and q value, but you have to switch the sign of whatever's after the x. The vertex is at p and q. Switch the sign of whatever's after the x. So the second one, the vertex is at -2, -1. We can tell some other stuff about the graph too. The first one, is it going to open up or down? Down, because it has a negative in front. The second one's going to open up. The first one, will it be wide or narrow compared to y equals x squared? Narrow, and the second one will be wide. I could ask you what the axis of symmetry is. I could ask you the maximum or minimum value. I could ask you the domain or range. And you should be able to tell me all of those things from just looking at the equation now. Because once you know the vertex and the direction of the opening, then you can figure out all those other things.